Welcome, everyone. Today, we're going to turn you into a full-fledged chemical detective. Think about it. Have you ever stared at a brightly colored piece of candy, an ordinary ink pen, or even a life-saving medication and wondered what's actually hiding inside of it? Like, is it completely pure? Is it perfectly safe? Or is it actually a dangerous cocktail of hidden chemicals? Well, in this explainer, we're going to master an incredible analytical technique known as paper chromatography. This is the exact real-world method that scientists and forensic investigators use every single day to uncover the hidden makeup of foods, medicines, and mysterious chemical mixtures. We're going to completely break down the underlying science, the rigorous physical setup, and the specific math that literally turns a simple, everyday piece of paper into a massively powerful forensic tool. Okay, let's dive into this. Here is our investigation briefing for today. We're covering 1. The ultimate chemical detective. 2. Setting up the perfect lab. 3. Decoding the chromatogram. 4. Cracking the RF code. 5. Revealing invisible substances. And 6. Avoiding rookie lab mistakes. Let's get right to it. Section 1. The ultimate chemical detective. Let's set up the core mystery of our entire investigation. When a professional scientist looks at a brand new pharmaceutical drug, a food additive, or, say, a mysterious liquid collected from a crime scene, the absolute most pressing question is always about purity. How do we actually know for sure if a substance is pure or if it's been dangerously adulterated with something else? To answer that, we rely on paper chromatography. At its core, chromatography is just an absolutely ingenious separation technique. It isolates and identifies the individual components of a complex mixture by taking advantage of their relative speeds as they travel through a medium. Imagine it like a microscopic tug-of-war, and the competitors are different chemical compounds. First, we place our chemical suspects on a piece of special paper. In chemistry terms, we call this paper the stationary phase because, well, it doesn't move. Then we introduce a solvent, something like water or ethanol, which is known as the mobile phase. As that liquid naturally creeps up the paper, it acts almost like a fast-moving river, pulling the chemicals right along with it. And here is where the magic happens. This creates a literal tug-of-war between the paper and the liquid. Substances that are highly soluble in the solvent but less attracted to the paper itself, they're going to win that tug-of-war. They race much faster and go significantly further toward the top. On the flip side, the chemicals with lower solubility in that mobile phase, or maybe a stronger physical attraction to the paper, they kind of drag their feet. By the end of this race, what started as a single confusing mixture has completely separated out into distinct, easily identifiable suspects. It's brilliant. Section 2. Setting up the perfect lab. So, we know the theory now. Now it's time to actually set the trap for our chemical suspects by building the perfect testing environment. Precision here is absolutely everything, right? A sloppy setup just means contaminated evidence. Let's walk through the physical setup, step by step, exactly as you'd need to lay it out for an IGCSE Chemistry exam or a real professional lab report. First up, you draw a horizontal baseline near the bottom of your chromatography paper. Second, you place a very, very small, concentrated spot of your test substance right on that line. You want it extremely small, because if you make a large, wet spot, it's just going to smear terribly as it travels up the paper. Third, you carefully stand the paper in a beaker that contains your solvent. Now listen closely, because it is absolutely critical that the initial solvent level sits below your baseline. If that liquid starts above the line, your carefully placed samples will just instantly wash off and dissolve directly into the beaker below, completely ruining the whole test. Fourth, you cover the beaker. This is a crucial little detail. Covering it saturates the atmosphere inside the beaker, which actually stops your solvent from evaporating off the paper halfway through the race. The solvent will quietly rise up the paper through a physical phenomenon called capillary action, carrying all those chemical dyes with it. And finally, and this is a big one, you must remove the paper before the solvent reaches the very top. You pull it out and immediately mark what we call the solvent front. That's the visible wet line showing exactly how high the liquid reached. You have to mark it before it dries and becomes completely invisible. So the crucial point in all of this setup is exactly how we draw that starting baseline. It honestly might seem like a tiny, insignificant detail, but it's a classic trap that catches countless students and amateur detectives every year. You absolutely must always use a graphite pencil to draw your baseline. Why? Well, think about it. If you use a standard ink pen, the ink itself will just dissolve in the solvent and run right up the paper alongside your actual samples. You'd literally be introducing a brand new suspect into your own lineup. Your entire investigation would be totally ruined before it even began, just clouded with rogue colors from your pen. Graphite, on the other hand, is this giant macromolecule that is completely insoluble in these typical laboratory solvents. It just stays exactly where you put it, making sure your results remain completely pristine and uncontaminated. Section 3. Decoding the chromatography. Once that paper has completely dried, we move right into the next phase of our investigation, which is decoding the visual clues left behind on what is now officially called a chromatogram. This is where we really learn to read those chemical fingerprints. And this brilliantly illustrates exactly what we're looking for. Notice how we distinguish between pure and impure substances. A purely single substance will only ever produce a single, lonely spot on the chromatogram. It doesn't matter what solvent you use or how long you run the test, one substance means one spot. But look at an impure mixture. Because it's literally made up of different, distinct chemical compounds that all have different solubilities, it naturally separates into multiple, distinct dots. The spot that traveled the highest, that one is the most soluble in that particular solvent. The one lagging way behind near the bottom, that's the least soluble. Simple as that. Let's put your new detective skills to the test with a really practical, real-world scenario. Imagine we're investigating the artificial food coloring used in 3 different brands of colored candies. We'll call them Sweet X, Sweet Y, and Sweet Z. By running a chromatogram, we can see exactly what chemical dyes these manufacturers are pumping into our food. Take a good look at the resulting spots. Ask yourself this: how many totally distinct, unique red dyes are present across all 3 of these sweets combined? Take a second, look closely, and see if you can crack it. Okay, let's reveal the answer by analyzing the matching spots across the sweets. The absolute golden rule of decoding a chromatogram is this: if 2 spots travel exactly the same distance up the paper in the same solvent, they are the exact same substance. So let's trace it out step by step. If you look at the lower red spots for sweets X and Z, they align perfectly horizontally, right? That is one distinct red dye. Now look a little higher up at sweets Y and Z. They share a completely different red dye that traveled much further up the paper. That's dye number 2. Because sweet Z contains both of those specific dyes, and sweets X and Y only contain one of each, we can conclusively say there are exactly 2 distinct red dyes used across all 3 of these products. This concept of horizontal alignment, it's absolutely crucial. It's the entire foundation of how we identify unknown mixtures by comparing them against known chemical standards. Section 4. Cracking the RF code. Visual alignment is great for a quick check, but real, rigorous science demands exact precision. Let's introduce the mathematical proof of our investigation, shifting from visual guesses to undeniable, objective data. We're talking about the RF value, which stands for retention factor. It's a really simple but incredibly powerful numerical value used to quantify exactly how far a substance travels relative to the solvent. You calculate it by taking the distance traveled by the substance and simply dividing it by the distance traveled by the solvent front. And remember, both of these distances absolutely must be measured from your pencil baseline. Now, you might be wondering, why do we need a ratio? Why not just use a raw measurement like 3 centimeters? Well, because a ratio means the exact size of your paper doesn't matter. Whether you run the test on a tiny 2-inch strip of paper or a massive poster-sized sheet, a specific chemical compound will always yield the exact same RF fraction under fixed conditions, meaning the same solvent and the same temperature. By calculating the RF of an unknown spot, we can take that number, check it against global standard data tables, and definitively identify exactly what the chemical is. Now, there is an absolute mathematical rule you need to keep in mind here. Your RF value will literally always be a fraction between 0 and 1. Think about the physical reality of our paper race. The chemical spot is being physically carried upwards by the moving solvent. Therefore, there's no way a spot can ever outrun the solvent that's carrying it. The distance of the substance will always be smaller than the distance of the solvent front. Also, because you are mathematically dividing a distance by a distance, like say dividing centimeters by centimeters, the units cancel each other out completely. The RF value is a pure, unitless ratio. Now, what's really interesting is how we can apply this to a life-saving real-world scenario, like pharmacology. Imagine we are looking at an impure sample of the common painkiller, paracetamol, which is actually synthesized in a lab from a precursor chemical called 4-aminophenol. In a chromatography test, you might see pure paracetamol running alongside a newly synthesized suspect sample. Let's say our suspect sample has a spot that matches the pure paracetamol perfectly at 2.60 centimeters. But, and this is a big but, It also has a contaminating spot lagging lower down at 1.70 centimeters. When you go to measure these distances, you absolutely must measure from the baseline to the very center of the spot, not the top edge, not the bottom edge, right to the center. By measuring to the center, we can calculate the exact RF value of that strange lower contaminant. In doing so, we can definitively prove that it's actually leftover unreacted 4-aminophenol. That tells the lab to destroy the entire batch of drugs so it doesn't reach the public until it's perfectly pure. It's literally life-saving math. Section 5. Revealing invisible substances. So far, we've honestly had it pretty easy. Our chemical suspects have all been brightly colored food dyes and colorful inks, but we are about to transition into a much more difficult complication at our crime scene. What happens when your chemical suspects leave absolutely no visible trace whatsoever? What if we want to separate complex biological mixtures, like amino acids or simple sugars? The physical separation process works exactly the same way. The solvent rises, the capillary action pulls the target molecules, and they separate out perfectly based on their solubility. But when you pull that paper out of the beaker and let it dry, it just looks completely blank. The biological substances are entirely colorless. So how on earth are we supposed to calculate an RF value if we literally cannot see the spots we're supposed to measure? To solve this invisible mystery, we use what's called a locating agent. Think of this as the exact chemical equivalent of a forensic investigator turning on a UV black light in a pitch-black room at a crime scene, just to reveal hidden evidence. After your chromatography paper is completely dry, you take it over to a fume cupboard and you spray it with this specific locating agent. The spray causes a rapid chemical reaction with the invisible spots, suddenly turning them into bright, highly visible colors, often deep purples, pinks, or even browns. You just wait for those colors to fully develop, and only then can you pull out your ruler and measure your distances to the center of those newly revealed spots. If you're studying for an exam, you should know that examiners don't usually require you to name a highly specific chemical like ninhydrin. They usually just want you to clearly state its core purpose. A locating agent is used to show the positions of colorless substances. Section 6. Avoiding rookie lab mistakes. Let's move to our final briefing. You now have the underlying knowledge of a master chemical detective, but let's be real, even the absolute best investigators can ruin a case with sloppy paperwork and bad habits. Let's see how this all builds together so you can avoid botching the test and losing easy exam marks. Here's a rapid-fire list of the absolute most common fatal errors examiners and professional lab techs see every single day. First, calculating an RF greater than 1. Remember, if you get 1.5, you flip the equation upside down, a spot cannot outrun the solvent. Second, measuring to the top of the spot instead of the center, which just completely throws off your mathematical accuracy. Third, writing a physical unit like centimeters right after your RF value. Remember, those distances cancel out into a pure unitless ratio. Fourth, taking the paper out and letting it dry before marking the solvent front with your pencil. Once that clear solvent evaporates, your denominator for the equation is gone forever. And finally, the ultimate rookie mistake, drawing your starting baseline with a standard ink pen and watching a rainbow of rogue colors bleed off the paper, totally ruining all of your hard work. We have covered a massive amount of ground in this explainer today, from the microscopic physics of capillary action and solubility tug-of-wars, all the way to calculating precise RF ratios and deploying invisible locating agents. You now know exactly how rigorous scientists decode the hidden chemical makeup of the world around us. But you know, this isn't just some technique reserved for high-tech, sterile laboratories. You can actually do this right now with a simple coffee filter, a graphite pencil, some tap water, and a few drops of food coloring, right in your own kitchen. So I want to leave you with this final thought. Grab some of the brightly colored markers or hard candies you have lying around your house. Apply your brand new detective mindset. Run a simple paper chromatogram and ask yourself, what invisible mixtures are hiding in plain sight in the very things you consume every single day? Stay curious, keep investigating, and thanks so much for joining me on this explainer.